All right, so we are going to review for mini exam 3 and mini exam 4. Oh my gosh, we're already in mini exam 4. So we'll do this similar to the last review video where I'll kind of pause at the beginning of each of our examples to give you a moment to try them out yourself, pause the video, and then you can restart and check your answers. So in this one we've got a mass of a 2-meter bar with density function of 250e to the negative x divided by 2. So all of that is the exponent on x, right? So I'll give you a chance to pause this if you wish. All right, so the mass is going to be the integral of the density function. And to find the integral of our density function, we are going to need to do substitution. So we get du is equal to -1/2 dx, or -2 du is equal to dx, and then our integral is going to be the integral of 250 times -2 e to the u du. I do want to go ahead and change the limits of integration, so I'm going to plug in 2, that's going to give me -1, and if I plug in 0, that's going to give me 0. So those are our new limits of integration. And our integral ends up being -500 e to the u from 0 to -1, -500 e to the -1 minus -500 e to the 0, or -500 over e plus 500, because e to the 0 is 1. And this is approximately, there's our exact answer up there, but it is approximately 316.06 grams. All right, let's take a look at the next problem that we have. Again, I will pause here for a second. All right, so we are looking at a spring, and it takes 30 newtons of force to stretch a spring 0.2 meters from its natural length. How much work is required to stretch the spring an additional 0.6 meters from that 0.2 meters? So they give us information about the spring at rest here. So if we've got our spring sitting here at rest, remember we start a number line here, and that at rest is 0. And we're looking at, my 0.2 did not end up looking very much like a 0.2, 0.4, 0.6, 0.8. So each of my lines there is 0.2. And they tell us the work to stretch it there to 0.2, or the force, excuse me. It is important to pay attention, and this is in newtons, so that tells me that that's force. Also, what we know is true about springs is that they satisfy Hooke's law, that the force required to stretch or compress that spring is K, which is some constant, times X, which is how far we stretch it. So we know that it's 30 newtons of force times whatever that K is, or K is equal to K times 0.2 meters. So we can use this fact to solve for K and figure out what the spring constant is for this situation. And for this situation, K is 150. And then our question is, how much work is required to stretch an additional 0.6 meters? So we want to stretch it all the way then to 0.8. So we want to go from 0.2 to 0.8. And our Hooke's law force function for the spring is 150x. And that's what we're going to take our integral of. And so we're going to get 75x squared from 0.2 to 0.8, and this is going to give us 45 joules of work. All right, let's take a look at the second question. Again, I'll take a moment if you want to pause the video. All right, so here they give us, so this is going to be a different spring, because here it's telling us how many joules of work is required to stretch the spring from its natural length of 0.2 meters. So it's the same distance, but this is a different spring. And they gave us the work instead of the force. And work is equal to the integral from A to B, so how far we stretch it, times that Hooke's law function, which is K times X dx. So again, we don't know K, that we need to figure out, but we do know that this integral would be equal to 30 if we were going from 0 to 0.2, and then whatever our force function is. So we can use this integral to solve for k. So we know that the integral, we would get k divided by 2 times x squared from 0 to 0.2 if we took the integral. And using the fundamental theorem of calculus, we get k over 2 is equal to 0.2 squared minus 0. So this gives us 30 is equal to k over 2 times, and I believe that is 0.04. And to solve for k, we just need to actually finish that multiplication there, divide by that 2/100ths, and we get that k in this case is 1,500. So we are going to find a similar integral as we did up above. It's still going to be from 0.2 to 0.8 because we're, again, trying to figure out how much work it is for that additional 0.6 meters. So we get 1,500 times x. That is going to be our force function in this case. And we're going to get 750 x squared from 0.2 to 0.8. And this is going to be equal to 450 joules for this spring. All right, let's take a look at the next question that we have. All right, so this one, we've got a 10-meter chain with a density of 0.5 kilograms per meter, hangs from a platform at a construction site that is 11 meters above the ground. So that chain doesn't reach all the way to the ground. Attached to the chain is a bucket full of nails. The bucket and the nails weigh 15 kilograms and that bucket's 1 meter tall. So how much work is required to lift the bucket to the platform? And we just want to set up the integral. So again, I'll take a moment and pause if you would like. All right, so our situation that we have here is that we've got our platform up here, and it is 11 meters from the ground. And then we've got our chain here, and it's sitting there at 1. It is only 10 meters, that chain. So it's going from the top, which is 11, down to 1. And then we've got our bucket that's full of nails, and that is a 1 meter tall bucket. So that is actually sitting on the ground. So we've talked about these before, that the bucket and the nails, that's going to be a constant amount of work the whole time. None of that's going to change because we're going to lift that bucket and those nails the whole time. So our bucket and nails is going to be our weight times our gravity, and then times how far we have to lift it, which is we have to lift it the whole 11 meters. So this is going to be 1,617 joules to lift the bucket. Then we want to know how much it is to lift the chain. So let's go back to green here. So the chain, that is getting lifted from 1 to 11. And actually, I do this all the time. I start by setting up the integral, and I don't like to do that first. I actually like to look and think about the force first. That helps me. And the force is going to be our density, which is that 1.5, times our gravity, which is 9.8, and then times the area that we're lifting here. So again, what we want to do is think about that we're going to take this chain and chop it up into bits here, and we're going to look at each little bit and how far we're lifting that little bit, and that each little bit there is got a width of delta x. So if we've got that x sub I star, it's got to move 11 minus x meters. So again, how that works here is this is the distance that amount of chain is going to travel. It's the 11 meters minus that x sub I star amount. So that's why we have 11 minus x sub I star. So here our integral for our work here is it is going to go from 1 to 11, where we were right there. And then we'll have 1.5, 9.8, and then our work, the x sub I stars turn into x, delta x turns into dx. So here's our integral that we're going to figure out. We're going to get 14.7 from multiplying those two coefficients out in front. And then we'll get 11x minus x squared over 2 from 1 to 11. And then let's see, doing our integral, just get some of the numbers here. So we'll get 735 joules to lift the chain. So then putting this together to lift our bucket and the chain, it is going to be 2,352 joules to lift all of those things together. All right, let's take a look at the next question that we have. Shoot. Sorry, I'm scrolling through here because, yep, I did what I thought I did. I have some notes in here, sort of a little out of order that I don't need. So sorry about the scrolling there that we did. But we're going to do some integral practice. Those ones that are on those slides, they are in here. So no worry, that's why I was scrolling through so fast. I forgot to take those other slides out. So here we are with our integration practice. So this one here, we've got x squared times cosine of 5x. Again, I will pause here for a second if you want to pause. All right, so this one we are going to do with integration by parts. And when we're doing this, we should take our algebraic function to be our u. So that makes that du is going to be 2x dx, taking the integral of u. dv is going to be our cosine of 5x dx. And then remember, we take the integral of both sides of this, and we get v is equal to 1/5 sine of 5x. Again, that 1/5 comes from doing substitution with cosine of 5x. And our integral is going to turn into, remember with integration by parts, it's u dv is equal to u times v minus the integral of v du. There we go. So it's going to be 1/5 x squared sine of 5x, again multiplying u times v, minus the integral of 1/5 sine of 5x, and then times our integral, or our du, which is 2x dx. So we actually have to use integration by parts a second time on this integral. And again, we're going to do a really similar setup, that we're going to have u be that algebraic function. So then we're going to get du is equal to 2x dx. And then our dv is going to be, oh, actually, I forgot about that 1/5 there. I like to, as I said in class when we first did this, I like to take that whole coefficient, so both the 1/5 and the 2, and put it in with my u, because then I just have to deal with sine of 5x dx there. And then we'll take the integral of both sides, and we'll get v is equal to 1/5. Nope, it's going to be negative because we're going to get cosine. So negative 1/5 cosine of 5x. All right, so our integral, we still have the 1/5 x squared sine of 5x. And then we have minus, and we have to be careful because we have to subtract all of this integral that we're going to do. So we're going to get u times v, and then minus the integral of negative 1/5 cosine of 5x. And then, oh, I have enough space, maybe quite, not quite. Let's see here, scoot this over. And then that's going to be times dx. All right, excellent. So now, finishing this up, again, that first part, nothing there that we need to do. We do need to distribute our minus sign through here. And so with our first term, we're going to get positive 2/25, because we've got the negative here, but then another negative, so that's going to turn that into positive, x cosine of 5x. And then we've got a negative and a negative there. So we'll have plus our integral of 2/25 cosine of, oops, and that is still negative, cosine of 5x dx. All right, so finally, and I don't want to write these again. Oops, I guess I actually have to hit copy, don't I? Copy, paste. And so we're going to actually get minus 2, oops, gotta make sure I'm a pen, 2/5 times another 1/5 sine of 5x plus c. And so again, of course, you can turn that into 2 over 125. All right, let's take a look at the next one here. Again, I'll pause for a second and let you take a look at it. All right, so this one, we are going to split this up a little bit and write this as the integral of sine squared of x cosine to the 4th, oh, my variable is theta on this one, theta cosine to the 4th of theta cosine of theta d theta. And maybe in this step here, we'll also change that cosine to the 4th power to be 1 minus sine squared of theta being squared. So remember our little quote substitution or trick that we're doing right there at that step is we're writing cosine squared of theta being squared, and then we're replacing that cosine squared with our 1 minus sine squared. So then we want to do a substitution of u being sine of theta, so that du is equal to cosine of theta d theta. Again, that's why here we peeled off one of those cosines from our cosine to the 5th power so that we could do our substitution. And we are going to end up with the integral of u squared 1 minus u squared being squared, and then du. And if you go ahead and FOIL out our 1 minus u squared, we do need to FOIL that out, and then distribute our u squared through, you're going to end up with u squared minus 2u to the 4th plus u to the 6th du. And I'm going to go up here to write this. So you're going to end up with 1/3 u to the 3rd minus 2/5 u to the 5th plus 1/7 u to the 7 plus c. And then substituting back, putting our sine function in everywhere it goes. Oh no, 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 space will go down here. Sine to the 7th power of theta plus c. All right, let's take a look at our next slide. We've got some more integrals to practice. All right, we've got a similar one now with tangent to the 9th and secant squared. So again, the idea here is that we want to kind of pull things apart a little bit and reserve the derivative of one of these two trig functions, secant or tangent, there we go. And we can easily pull off a secant squared, and then we could trade this secant squared that we have to be tangent squared of x plus 1. So we've got everything in terms of tangent except for that secant squared, and that's what we want because then we can have u being tangent of x, and then du is secant squared of x dx. So again, this whole part here that we reserved as a secant is there for us to do our substitution. And so we're going to get the integral of u to the 9th, u squared plus 1 du. Or if we multiply this out, we get u to the 11th plus u to the 9th du. We'll go up over here. We get 1/12th u to the 12th plus 10th, I want that to be 11th, u to the 10th plus c, and substituting back in, we get 1/12th tangent to the 12th power of x, and then 1/10th tangent to the 10th power of x plus rc. All right, again, we'll take a moment if you want to hit pause and try out the next one. All right, so this next one, when we see a square root where we've got a perfect square and x being either subtracted or added, that's telling us that we're going to have a trig substitution. So we're going to want to draw a triangle here. And the triangle that we're going to want to use here with this question is where our opposite side is that x squared minus 9. So I need to move my notes here. X squared minus 9, and then x is our hypotenuse and 3 is our adjacent side. So what's going to be true here? We're going to have x being equal to 3 secant of theta. The square root of x squared minus 9 is going to be equal to 3 times tangent of theta, and dx is going to be equal to 3 times secant of theta, tangent of theta, d theta. Again, remember that comes just from us taking the derivative of that first statement. So now we can use all three of these to substitute into our equation here, and I'll do some quick underlining to help us see where everything is going to substitute, and that we're going to get the integral of 3 tangent of theta divided by 3 secant of theta times 3 secant of theta tangent of theta d theta. And then we have a whole bunch of things that end up canceling in this, which is really nice. So those 3's cancel, those secants cancel, and we end up with the integral of 3 times tangent squared of theta d theta. We've seen this one a couple of times, and the best thing to do is to actually turn this into secant of theta minus 1 d theta, because if we have that, then we end up with that the integral of secant squared is tangent, and then the integral of that 1 is going to be theta, and I just distributed 3 through. So that we don't forget to do that part of it, and then plus c, and now it's time for us to, back substitute. So we've got 3 tangent of theta, and we know exactly what that is up here. That is our square root of x squared minus 9. Our 3 theta right here, theta, we can write that and figure out what that is using our first statement there, that x over 3 is equal to secant of theta, and that the inverse secant of x over 3 is equal to theta. This is not the only way for us to figure out theta. We have other options, so remember that. So we get negative 3 inverse secant of x over 3 plus rc. All right, let's take a look at the next set of integrals that we have. All right, so again, I'll pause here for a second. All right, so we've got sine or secant of x times tangent of x over 2 plus secant of x. So kind of my first thought is always trying to just use substitution, because sometimes it actually works, and when it does, it's so nice and so easy. And this is one of those cases where substitution, just substituting what's in that denominator of that kind of rational type function there, our 2 plus secant of x, we're going to be able to exactly do a really straightforward substitution. That should be a du. Here we go. And get 1 over u du, which is the natural log of the absolute value of u, which is the natural log of the absolute value of 2 plus secant of x plus c. All right, and while I fix my handwriting here, if you want to pause and try out the next one, feel free. All right, I tried to save us some space there so that I could do a couple of things. Number one, write our formula for integration by parts up here. Ooh, I cannot draw a u right now to save my life. There we go. U times v minus integral of v du. There we go. So we are going to do integration by parts because, again, we have 2 functions that are being multiplied, neither of which is the derivative of the other. So that's kind of the situation that we're stuck in. We should take that algebraic function, x squared, that should be our u. So that makes du 2x dx. And then we should have, again, what's left in our integral, that should be our dv, e to the 4x dx. And then taking the integral of both sides of that, we get v on the left-hand side, and then 1/4 e to the 4x. Again, that's coming from the fact that there's a 4x there, that we've got to do substitution. So now this turns our integral into 1/4 times x squared times e to the 4x. Again, that's just from us doing our u times our v. And then minus, oops, I don't want to be the highlighter. Here we go, minus the integral of u times 2x dx, because that's our dv. So where we are is we're sitting in a situation where we're going to have to use integration by parts again to take the integral of this second part here, just like we had in that first one. So again, what we should do is take any coefficient that we have and the algebraic function and have that be our u. So we've got 1/4 times 1/2. That does give us, or 1/4 times 2, which gives us 1/2. There we go. So we got du is equal to 1/2 dx. And then our dv is going to be all the stuff that's left, which is 4x in dx. The nice thing about doing these with exponential functions is we got the exact same thing for dv, so we've already done this integral. There's not a lot of like thinking that we have to do, and I always appreciate that when we can kind of go on autopilot just a little bit here. All right, so now what this makes our integral, this first part, that's the part that's already done, so we don't need to worry about that. We do need to subtract and put brackets there. So we're going to have, again, now our new u times our v minus the integral of v times our du, which is 1/2 dx. So let's see if we can kind of simplify this and find our integral at the same time here. So we'll get minus 1/8 x e to the 4x, and we're also needing to remember to distribute our minus sign to both of our terms here. And then we're going to get plus the integral of, see, we're going to have a 1/8 and then another 1/4 e to the 4x plus c, because again, we just are ending up taking that integral of e to the 4th now for a third time. Actually, yeah, it's for a third time. It's like, do we do it more than that? Nope, it was for a third time. And we've already simplified these two parts. So, oops. So we can, if I could hit the copy before it disappears, there we go, paste that there. Whoa. And we end up with plus 1/32 e to the 4x plus c. All right, I think I have one more integral for us to try. Right, so again, take a moment if you would like. So I might do just a little bit of rewriting on this to help us see what we actually have here. That exponent of 3/2, that is really the square root of that denominator to the third power. So we've got a perfect square plus another perfect square underneath a square root. So that is telling me that we can do a trig substitution. And when it's addition, that's where we make our hypotenuse, that x squared plus 25. We're going to do the adjacent side as 5 and the opposite side as x. So this is going to give us that x is equal to 5 times tangent of theta. Square root of x plus 25 is equal to 5 times secant of theta. And again, we're using with the trig substitutions, we're generally, sorry, I'm trying to erase this and talk at the same time. Never try to do two things at once. We're using tangent and secant and sine as much as possible, mainly because when we take the derivative, we don't get negative numbers. It keeps things positive. You can always set these up a different way and they will work out and you will get the correct answers. All right, so again, sort of substitution wise, what we're going to do is we're going to use this one. That's going to go on the bottom of our fraction. And then we're also going to use this dx. That's going to go right here. So you don't necessarily remember use all of these all the time. It kind of depends on what's actually in your integral. So we're going to get 1 over 5 times secant of theta to the third power, and then times 5 times secant squared of theta d theta. So there's a lot of things that cancel here. We've got 5 to the third power, and we've got secant to the third power, and then 5 secant squared of theta d theta. So what all is going to cancel here? we are going to end up with, let's see, 2 of those there. I'm just going to cancel with 1 of those on top there. And 2 of these here, I'm going to cancel with all of those. So we are going to end up with 1/25th as a coefficient, and we're going to end up with 1 over secant of theta, d theta. And remember that secant is 1 over cosine, so 1 over secant is cosine. So we're going to end up with 1/25th sine of theta plus c. And let's see, is there anything more that we need to do with this? Yeah, we got to get it back in terms of x. And so we need to know what sine of theta is. Well, we get that from our triangle. Sine of theta is our opposite side over our hypotenuse. So that's going to be x over the square root of x squared plus 25. So we're going to get 1 over 25 times x over the square root of x squared plus 25 plus c.